What if I told you the universe isn't just a chaotic expanse of stars and emptiness, but a carefully structured masterpiece filled with architectural wonders that rival the grandest creations on Earth? Picture this: galaxies aren't scattered randomly but woven into vast, delicate webs, stretching across billions of light years like threads in a cosmic tapestry. These aren't just pretty patterns, they're the blueprints of reality itself, holding clues to everything from the birth of the first stars to the ultimate fate of existence. And today, we're stepping into the role of cosmic explorers, uncovering 34 of the most breathtaking structures the universe has to offer. Think about the last time you stood beneath a towering skyscraper or an ancient cathedral, feeling small yet connected to something monumental. Now multiply that awe by a factor of 1 trillion. Out there, beyond our atmosphere, lie formations so immense they could swallow entire galaxy clusters without a trace. Structures like the Great Wall, a sprawling chain of galaxies over 500 million light-years long, or the mysterious dark matter filaments that act as invisible scaffolding for the cosmos. These aren't just scientific curiosities, they're the pillars of our cosmic home, shaping everything from the paths of stars to the very fabric of space and time. But here's the most mind-bending part: these architectures aren't static. They're alive with motion, evolution, and even violence. Black holes spin like celestial whirlpools, dragging space itself into their grasp, while nebulae paint the void with colors so vibrant they seem unreal. And the deeper we look, the more we realize the universe isn't just building these structures. It's telling us a story about how we came to be, how matter learned to dance, and how the tiniest quantum fluctuations grew into the grandest designs imaginable. By the time we're done, you won't just see the cosmos as a void filled with stars. You'll see it as a living, breathing cathedral, and you'll know exactly where we stand within its walls. So, are you ready to take the first step? Let's begin. The cosmic web isn't just a structure, it's the universe's backbone, an invisible framework that dictates where galaxies form, how they move, and even how they collide. Imagine holding a sponge in your hand, its delicate latticework of holes and fibers mirroring the way galaxies cluster along dark matter filaments, with vast, empty voids stretching between them. These voids aren't just empty space, they're cosmic deserts, some so large you could fly through them for hundreds of millions of light years without encountering a single star. Yet, it's within the dense intersections of these filaments where the most spectacular galactic cities thrive, like the Laniakea Supercluster, home to our own Milky Way, where hundreds of thousands of galaxies swirl in a gravitational dance. What's truly astonishing is how this web came to be. In the earliest moments after the Big Bang, the universe was nearly smooth, with only the tiniest ripples in the fabric of space-time. But over billions of years, gravity took those faint whispers of density and sculpted them into the towering walls and threads we see today. Dark matter, the mysterious, invisible substance making up most of the universe's mass, acted as the scaffolding, its gravitational pull drawing ordinary matter into the patterns we now observe. Supercomputer simulations like the famous Millennium Run recreate this process in stunning detail, showing how galaxies are born where these filaments intersect, like beads strung on a necklace. But here's the twist: we've only seen a fraction of this web directly. Most of it remains hidden, mapped indirectly through the galaxies that trace its outline or the faint distortions of light caused by its gravity. Projects like the Dark Energy Survey are slowly filling in the blanks, revealing how the cosmic web stretches and evolves over time, and if we could see it in full. It would be like uncovering the blueprints of existence itself, a roadmap showing how everything, from the smallest star to the largest supercluster, fits into the grand design. The cosmic web isn't just a relic of the past either. It's still growing, still shaping the universe in ways we're only beginning to comprehend. Every galaxy, every star, even our own planet, owes its existence to this vast, intricate architecture. Galactic superclusters are the metropolises of the cosmos, vast, glittering cities where galaxies gather in unimaginable numbers, bound together by the unbreakable chains of gravity. Take our own cosmic neighborhood, the Laniakea supercluster, a sprawling megastructure so enormous that light would need 520 million years just to cross from one end to the other. Within its borders, more than 100,000 galaxies whirl through the darkness, including our Milky Way, each one a glittering island of stars. But Laniakea isn't just sitting still. It's in motion, drifting along invisible rivers of gravity toward an even greater anomaly known as the Great Attractor, a mysterious region of space pulling entire superclusters into its grasp. Then there's the Shapley supercluster, a behemoth so dense and massive that it warps the very fabric of space-time around it. Imagine tossing a stone into a pond and watching the ripples bend outward. That's what Shapley does to the universe. Its gravity so strong it can redirect the paths of galaxies millions of light years away. These superclusters aren't just passive landmarks, they're active players in the cosmic drama, their immense gravity shaping the large-scale structure of the universe. Some scientists believe they might even hold clues to one of the greatest mysteries of all: why the expansion of the universe is accelerating. Here's how it works. Dark energy, the mysterious force driving the universe apart, seems to be locked in a tug of war with gravity. In regions like Shapley, where matter is densely packed, gravity temporarily wins, slowing down expansion locally. But in the vast voids between superclusters, where matter is scarce, dark energy dominates, stretching space faster and faster. This cosmic push and pull creates a dynamic, ever-changing landscape where superclusters act like anchors, briefly resisting the universe's rush to expand before ultimately being swept along. What's truly humbling is realizing that these structures are just one level in a hierarchy of cosmic architecture. Superclusters themselves are often part of even larger formations, like the Pisces-Cetus supercluster complex, a web of galaxies spanning over 1 billion light-years. It's a reminder that no matter how vast something seems, the universe always has a way of making it feel small. And yet, within these titanic assemblies, galaxies still manage to retain their individuality, each one a unique masterpiece of stars, dust, and possibility. The dance of superclusters isn't just a spectacle, it's a story of connection, showing how even the mightiest structures in existence are bound by the same invisible threads that tie the cosmos together. Dark matter halos are the universe's silent architect, structures so invisible, so elusive, yet so powerful that without them, galaxies as we know them wouldn't even exist. Picture a spiderweb, its delicate threads unseen until dew catches the light. That's dark matter, an invisible framework holding galaxies together. It's gravity, the glue preventing stars from scattering into the void. Every galaxy, from the tiniest dwarf to the grandest spiral, is cradled within one of these halos, their gravity dictating how stars move, how gas collects, even how galaxies collide and merge over cosmic time. But these halos aren't just smooth, featureless clouds. Cutting-edge simulations reveal they're teeming with substructure, smaller clumps of dark matter orbiting within them like ghosts in a cosmic machine. These clumps, some no larger than a star cluster, are remnants of the universe's earliest days, surviving billions of years without ever interacting with ordinary matter. Some scientists speculate they could be hiding something even stranger, exotic particles, or perhaps portals to dimensions we can't yet perceive. The sheer strangeness of dark matter forces us to rethink everything we know about physics. Here's where it gets even weirder. Dark matter doesn't just shape galaxies, it shapes how we see them. When light from distant stars passes through a halo, its path bends, warping our view of the cosmos like a funhouse mirror. Astronomers use this effect, called gravitational lensing, to map these invisible structures, revealing halos far larger than the galaxies they host. Some halos stretch millions of light-years across, their gravity pulling in galaxies like moths to a flame. Yet for all their influence, we still don't know what dark matter actually is. Is it a sea of undiscovered particles, a shadow universe overlapping our own? Every experiment, from deep underground detectors to particle colliders, brings us closer to an answer or deeper into the mystery. One thing's certain, dark matter halos aren't just cosmic curiosities. They're the hidden hands that built the universe, and their secrets could rewrite the story of existence itself. Black hole jets are nature's ultimate particle cannons, twin beams of superheated plasma screaming across space at nearly the speed of light, so powerful they can punch through entire galaxies. Take the jet erupting from the black hole at the heart of Galaxy M87, stretching over 5,000 light-years into the void. That's like a laser beam shooting from Earth past the nearest star system, Alpha Centauri, and continuing 50 trillion times further. But what's truly staggering isn't just their size, it's their energy. These jets can outshine every star in their host galaxy combined, turning black holes from cosmic vacuum cleaners into some of the brightest engines in the universe. The secret lies in the chaos surrounding a black hole's event horizon. As matter spirals inward, it doesn't just vanish quietly. It forms a seething, magnetized disk hotter than a million suns. Twisted magnetic fields, amplified by the black hole's furious spin, act like cosmic railguns, channeling some of this infalling material away from the poles at relativistic speeds. Imagine water spiraling down a drain, only for a fraction to get whipped upward by an invisible force, transformed into a blistering geyser. That's essentially what happens here, except the water is plasma heated to billions of degrees, and the geyser could vaporize entire solar systems in its path. What's fascinating is how these jets sculpt their surroundings. They carve colossal bubbles in intergalactic gas, shock waves rippling through galaxy clusters like tsunamis. In some cases, they even regulate star formation, heating nearby gas so intensely it can't collapse into new stars. The Perseus cluster, for instance, bears the scars of ancient jets that blew titanic cavities in its hot gas, each bubble large enough to swallow our Milky Way whole. But these jets aren't just destructive, they're also cosmic recyclers, injecting heavy elements forged near the black hole back into intergalactic space, seeding future generations of stars and planets. The real mystery, how something so chaotic produces jets so precise. Despite the turbulence of the accretion disk, these beams remain collimated over staggering distances, barely spreading out even after thousands of light years. Some theories suggest magnetic fields act like a nozzle, keeping the plasma tightly focused, while others propose subtle interactions with the fabric of space-time itself. Every new observation, like the Event Horizon Telescope's groundbreaking images, peels back another layer of the puzzle, revealing a universe where even the most violent phenomena obey an underlying order. Black hole jets don't just defy expectations, they rewrite the rules of physics on scales we're only beginning to comprehend. Neutron star mergers are the universe's ultimate gold factories, violent, glittering collisions where the heaviest elements in existence are forged in a heartbeat. Picture two city-sized stars, each so dense a teaspoon of their material would weigh 1 billion tons, locked in a death spiral. As they finally crash together, the impact unleashes more energy in seconds than our sun will produce in its entire lifetime. But it's not just about raw power. These mergers are cosmic crucibles, where the chaotic aftermath births elements like gold, platinum, and uranium, scattering them across the cosmos like precious seeds. The proof came in 2017, when gravitational wave observatories detected a ripple in space-time labeled GW170817. Telescopes swiveled to the source, capturing the first ever visible light from a neutron star collision, a kilonova, a flare of radiation so packed with heavy elements its glow outshone entire galaxies. Spectroscopic analysis revealed something astonishing. The event had ejected enough gold to outweigh our planet several times over. Suddenly, the mystery of where Earth's precious metals came from had an answer. That ring on your finger, the platinum in your electronics, all of it was likely forged in a cataclysm like this, billions of years ago. What makes these mergers so special isn't just their rarity, it's their precision. Unlike supernova, which scatter elements unevenly, neutron star collisions eject material in focused, high-velocity jets. Simulations show these jets act like cosmic spray cans, painting nearby galaxies with heavy elements in concentrated bursts. This could explain why some star systems are richer in gold and platinum than others. It all depends on whether a neutron star merger happened nearby during their formation. But here's the twist: these events might be even more consequential than we thought. Some theories suggest they could be the primary source of rare Earth elements essential for modern technology, like neodymium and europium. Others speculate they might trigger waves of star formation, their shock waves compressing nearby gas clouds into new stellar nurseries. And then there's the lingering question of frequency. Current estimates suggest a merger happens somewhere in the universe roughly every 10,000 to 100,000 years. But with gravitational wave detectors growing more sensitive, we're likely to find they're far more common than we ever imagined. Every new detection peels back another layer of this cosmic mystery. Did neutron star mergers provide the raw materials for Earth's formation? Could they have seeded life itself with essential heavy elements? Each collision we observe isn't just a spectacle, it's a time capsule, revealing how the universe transforms simplicity into complexity, chaos into creation. The gold in your jewelry, the uranium powering reactors, even the iodine in your body, all of it traces back to these fleeting, violent moments where stars die so that new worlds can live. Pulsar planets are the universe's ultimate survivors, worlds that shouldn't exist, clinging to life in the most unforgiving environments imaginable. Take PSRB 1257+12, a pulsar over 2,000 light-years away with not one, but 3 planets locked in its deadly embrace. These aren't just any dead star systems, they're the first exoplanets humanity ever discovered, back in 1992, shattering our assumptions about where planets could form. Imagine a world where the sky is lit not by a sun, but by a rapidly spinning corpse of a star, blasting out beams of radiation so intense they could strip away an atmosphere in seconds. Yet somehow, against all odds, these planets endure. The conditions around a pulsar are nothing short of apocalyptic. When a massive star goes supernova, its core collapses into a neutron star so dense it packs the mass of our sun into a sphere the size of a city. Some of these neutron stars become pulsars, spinning hundreds of times per second, their magnetic fields accelerating particles to near light speed, creating lethal beams of X-rays and gamma rays. Any planet caught in this crossfire is bathed in enough radiation to vaporize rock, Yet pulsar planets like Pulsar b 1620-26b somehow persist. Scientists believe they might be the shattered remnants of giant planets, their outer layers blasted away, leaving behind dense, metallic cores, cosmic nuggets hardened in the furnace of a supernova. But here's the real shocker: some of these worlds might even hold onto atmospheres. Theoretical models suggest that under the right conditions, a pulsar planet's magnetic field could deflect enough radiation to allow a thin layer of gas to survive, possibly even one rich in exotic elements like neon or argon. And if there's an atmosphere, could there be, against all logic, life? It's not impossible. On Earth, we've found extremophiles thriving in nuclear reactors and boiling acid, organisms that laugh in the face of conditions we once thought unsurvivable. If life can cling to hydrothermal vents at the bottom of our ocean, why not under the flickering glow of a pulsar? The bigger lesson here isn't just about these bizarre worlds, it's about redefining what we consider habitable. For centuries, we've imagined life needing conditions just like Earth's, but pulsar planets force us to think bigger. Maybe life doesn't need a yellow sun and liquid water. Maybe it can evolve in molten metal oceans, powered by radiation instead of sunlight, or deep in the cracks of a planet squeezed by crushing gravity. Every pulsar planet we discover is a reminder that the universe is far stranger, far more creative than we ever imagined. And if life can find a way here, in the harshest corners of existence, where else might it be hiding? Quasars are the universe's ultimate time capsules, beacons so bright they pierce through cosmic history, illuminating secrets from when the cosmos was just a toddler. Imagine a single object no larger than our solar system, pouring out more light than 1,000 Milky Ways combined. That's the raw power of a quasar, fueled by a supermassive black hole feasting on gas at the heart of a young galaxy. The light we see from these objects today began its journey when Earth was still molten rock, carrying snapshots of an era when galaxies were wild, chaotic places. What makes quasars truly extraordinary isn't just their brilliance, it's what they reveal about the universe's adolescence. By studying their spectra, astronomers have uncovered clouds of pristine gas from before the first stars formed, pockets of the universe untouched by heavy elements. Some quasars even cast shadows, their light absorbed by intervening hydrogen clouds, creating dark bands in their spectra like tree rings recording cosmic droughts. These patterns tell us how the early universe reionized, transitioning from a fog of neutral hydrogen to the transparent expanse we know today. But here's the puzzle. If quasars were so common billions of years ago, why do they seem to vanish in the modern universe? The answer lies in their appetites. As galaxies mature, their central black holes eventually consume most nearby gas, starving themselves into silence. Others may blow away their fuel reserves with powerful jets, like a candle extinguishing its own flame. The brightest quasars likely burned out fastest, their furious feasting leaving behind dormant giants like Sagittarius, a star, the quiet black hole at our Milky Way's core. Yet even in their absence, quasars shape the cosmos. Their radiation may have stifled star formation in early galaxies by ionizing surrounding gas, while their outflows enriched intergalactic space with heavy elements. Some researchers speculate they even influenced the large-scale structure of the universe, their energy carving bubbles in the cosmic web that guided galaxy formation. Modern telescopes like the James Webb Space Telescope are now spotting hidden quasars shrouded in dust, proof that these cosmic lighthouses never truly disappeared, only dimmed. The legacy of quasars isn't just in their light, but in the questions they force us to ask. Did they help or hinder the rise of life by regulating star formation? Could their fading mark a universal transition from chaos to order? Every quasar we study is a message in a bottle from the universe's youth, whispering clues about how chaos forged the structures we see today. Gamma-ray bursts are the universe's most violent flashes, cosmic explosions so intense they outshine entire galaxies in the blink of an eye. Imagine compressing all the energy our sun will ever produce into a beam no wider than a city block, then firing it across the cosmos at nearly the speed of light. That's the raw, terrifying power of a gamma-ray burst, a phenomenon so bright it can be seen billions of light years away, yet so fleeting some last barely a second. These bursts come in two flavors, each with its own apocalyptic origin story. The long-duration bursts, lasting more than 2 seconds, are the death cries of massive stars. When a star 20 times heavier than our Sun exhausts its fuel, its core collapses not into a neutron star but into a black hole. As matter plummets inward, twin jets of plasma erupt from the poles, slicing through the star like cosmic blowtorches. What follows is a supernova on steroids, a hypernova where the star's outer layers are obliterated in a fireball of gamma rays. The short bursts, lasting less than 2 seconds, are even more extreme. They're thought to arise from neutron star collisions, those same gold-forging crashes we explored earlier. When two ultra-dense stellar corpses merge, the resulting black hole can launch jets so focused, so energetic, they briefly outshine every other source of gamma rays in the observable universe. But here's what makes these bursts invaluable to science: their afterglows. Like embers cooling after a wildfire, the jet's heat surrounding gas, creating a fading glow across multiple wavelengths. This afterglow acts as a cosmic yardstick, allowing astronomers to measure distances to the farthest corners of the universe. The record holder, GRB 090429b, erupted when the universe was just 600 million years old, a baby by cosmic standards. Its light traveled over 13 billion years to reach us, carrying clues about the conditions of the early cosmos. Now for the elephant in the room: could one of these bursts ever threaten Earth? The odds are vanishingly small, but not zero. A gamma-ray burst within a few thousand light-years could strip away our ozone layer, exposing life to deadly ultraviolet radiation. Some scientists speculate such an event might have contributed to the Ordovician mass extinction 450 million years ago, when 70% of marine species vanished. The good news: our galaxy lacks the dense star-forming regions where these bursts typically occur, and we'd likely see the warning signs, a nearby supernova or neutron star merger, long before the gamma rays arrived. What's truly humbling is realizing these bursts aren't just destructive. They're creative forces too. The same jets that could sterilize a planet also seed the cosmos with heavy elements, while their energy might even trigger star formation in distant gas clouds. Gamma-ray bursts are a reminder that the universe doesn't operate in absolutes. It's a place of balance, where destruction and creation are two sides of the same coin. And as we detect more of these flashes, we're not just studying cosmic explosions. We're piecing together the story of how the universe grows, changes, and occasionally reminds us of its unimaginable power. Gravitational lenses are the universe's ultimate magnifying glasses, natural distortions in space-time so powerful they can bend light like a prism, revealing galaxies too faint or distant for any telescope to see unaided. Picture a marble resting on a stretched rubber sheet. The depression it creates warps the path of anything rolling past. Now replace the marble with a galaxy cluster weighing a quadrillion suns, and the rubber sheet with the fabric of space itself. Light from a background galaxy, traveling toward us for billions of years, curves around this cosmic well, splitting into multiple images or stretched into luminous arcs. The result: nature's own telescope, free of charge, amplifying the faintest whispers of the early universe. Einstein's theory of relativity predicted this phenomenon over a century ago, but even he doubted we'd ever observe it. Today, gravitational lensing isn't just real, it's revolutionizing astronomy. Take Hubble's Frontier Fields project, where clusters like Able 1689 acted as colossal lenses, magnifying galaxies so distant their light dates back to when the universe was barely 500 million years old. Without this cosmic assist, those galaxies would remain invisible, their starlight too dim to register even on Hubble's sensitive detectors. But lensing does more than magnify. It distorts in ways that unveil hidden truths. By analyzing the warped shapes of background galaxies, astronomers can map the distribution of dark matter in the foreground cluster, invisible mass revealed by its gravitational fingerprint. The most striking examples push the limits of imagination. The El Gordo cluster, 7 billion light-years away, lenses a galaxy so far behind it that we see the galaxy as it appeared just 1 billion years after the Big Bang, a time when the first stars were still flickering to life. Even more mind-bending are Einstein rings, near-perfect circles of light formed when a distant galaxy aligns precisely behind a massive foreground object. These rings aren't just beautiful, they're precision tools allowing scientists to measure cosmic distances and the universe's expansion rate with unprecedented accuracy. But the real excitement lies in what's next. Upcoming telescopes like the Nancy Grace Roman Space Telescope will exploit lensing to hunt for primordial galaxies from the universe's dark ages, a time before stars lit up the cosmos. Others might uncover rogue planets or dark matter clumps by spotting the subtle twinkles they create as they drift in front of distant stars. Gravitational lenses even offer a cheat code for studying exoplanets when a star lenses another. Any planets orbiting the foreground star can briefly amplify the light further, betraying their presence. What's humbling is realizing these lenses aren't just tools, they're cosmic accidents. The alignment of galaxies across billions of light-years is pure chance, a fleeting intersection of paths in an ever-expanding universe. Yet in these rare moments, the universe hands us a key to its deepest secrets, bending light not just through space, but through time itself. Every lensed galaxy is a message from two eras at once: the age of the foreground cluster that bends the light, and the far older epoch of the background galaxy whose light it magnifies. Together, they remind us that the cosmos isn't just vast, it's interconnected, with gravity weaving threads between objects that we'll never truly touch. Dark energy isn't just a mystery, it's the universe's greatest magic trick, an invisible force working against gravity's pull to stretch space itself faster and faster. Imagine blowing up a balloon with tiny dots on its surface. Normally, you'd expect those dots to drift apart slowly as the balloon expands. But with dark energy, it's as if someone suddenly starts pumping air harder, making the dots accelerate away from each other. That's exactly what's happening on a cosmic scale. Galaxies that should be coasting apart gently are instead racing into the void, their speed increasing over billions of years. And here's the kicker: we have no idea why. The shock of this discovery came in 1998, when two teams studying distant supernova made an unsettling observation. These exploding stars, used as cosmic yardsticks, were dimmer than expected, meaning they were farther away than the universe's known expansion rate could explain. The only possible conclusion: the expansion wasn't just continuing, it was speeding up. This revelation flipped cosmology on its head, earning its discoverers the Nobel Prize and forcing scientists to confront a staggering truth. 70% of the universe's energy budget is tied up in something we can't see, touch, or even define. What makes dark energy so baffling isn't just its dominance, it's how it behaves. Einstein's cosmological constant, a mathematical placeholder he once called his greatest blunder, offers one explanation. Dark energy could be an unchanging property of empty space itself, a steady pressure woven into the fabric of reality. But there's a competing idea quintessence, a dynamic field that might fluctuate over time, strengthening or weakening as the universe ages. If true, this could mean dark energy's influence isn't set in stone. It might have sculpted the early universe differently than it shapes the cosmos today, and its future effects could be even more dramatic. The stakes couldn't be higher. If dark energy remains constant, the universe faces a big freeze, galaxies racing beyond the cosmic horizon until every star system is isolated in an ever-cooling void. But if it grows stronger, we could get a big rip, where even atoms are torn apart in a final, violent burst of expansion. There's even a fringe possibility that dark energy could reverse, turning from repulsive to attractive, pulling the universe back into a cataclysmic collapse. The difference between these futures hinges on a number called the equation of state parameter, essentially, how much dark energy's pressure changes as space expands. Pin that down and you unlock the universe's ultimate fate. Right now, projects like the Dark Energy Survey and the upcoming Euclid Space Telescope are mapping billions of galaxies to trace expansion's history in unprecedented detail. By studying how galaxy clusters form and how light bends around them, they're piecing together dark energy's fingerprint. Meanwhile, lab experiments hunt for subtle shifts in fundamental constants that might betray dark energy's presence at microscopic scales. It's a race against time, not just cosmic time, but our own. Every second, dark energy pushes more of the observable universe beyond our reach, galaxies vanishing over an invisible horizon like ships sailing off the edge of a flat Earth. The irony is delicious. The more we learn about dark energy, the more we realize how little we understand. It's as if the universe handed us a riddle wrapped in a paradox, a force that dominates everything yet leaves no trace, an energy that shapes destiny but resists definition. And somewhere in that mystery lies an answer not just about how the cosmos expands, but why it's built this way at all. Dark energy isn't just a chapter in astrophysics, it's the question mark at the end of the universe's story. And whether that story ends with a whisper, a scream, or something we can't yet imagine, depends entirely on the secrets we're just beginning to uncover. The Great Attractor is the universe's ultimate tug of war, an invisible force dragging our entire galaxy, along with thousands of others, through the cosmos at a staggering 14 million miles per hour. Picture this: you're floating in a river pulled by a current you can't see toward a waterfall hidden just beyond the horizon. That's the Milky Way's predicament, caught in a gravitational grip so powerful it overrides even the expansion of the universe itself. And the strangest part, we can't even see what's pulling us. For decades, this cosmic mystery lurked behind the Milky Way's zone of avoidance, a thick band of dust and stars obscuring nearly 20% of our view. It wasn't until the 1970s that astronomers noticed something bizarre. Every galaxy in our local supercluster, including Andromeda and the Milky Way, was streaming toward the same patch of empty space near the constellation Centaurus. The culprit, a gravitational anomaly so massive it could only be one thing: a previously unknown structure, later dubbed the Great Attractor. At first, scientists assumed it was just a dense cluster of galaxies, perhaps the Norma cluster, which sits roughly in the same direction. But the math didn't add up. The pull was too strong, too focused. Then came another twist. The Great Attractor itself seems to be moving, tugged toward something even larger. The Shapley Supercluster, a behemoth 650 million light-years away containing tens of thousands of galaxies. This realization turned the mystery inside out. The Great Attractor isn't the end of the chain. It's a waypoint in an even grander cosmic flow, like a stepping stone in a river leading to a vast, unseen ocean. So what exactly is it? The leading theory suggests it's a confluence of several superclusters, their combined gravity creating a focal point for everything around us. Infrared and radio telescopes which peer through the Milky Way's dust have revealed hints of this structure, galaxies packed so tightly they bend the fabric of space like a bowling ball on a trampoline. But there's a wild card, dark matter. Some models propose the Great Attractor's pull can't be explained by visible matter alone. Could it be anchored by an enormous, invisible knot of dark matter, a gravitational nexus where the cosmic web's filaments intersect? The answer might lie in the next generation of telescopes, projects like the Square Kilometre Array, with its unprecedented sensitivity to radio waves, could map the hidden galaxies behind the Milky Way in exquisite detail. Meanwhile, gravitational wave detectors might sense the ripples from black hole mergers in the region, offering indirect clues about its mass. Every new observation peels back another layer of this enigma, revealing not just the Great Attractor's identity, but how it fits into the universe's larger story, a story where even the mightiest structures are mere players in a gravitational ballet spanning billions of light years. What's humbling is realizing this isn't just about some distant anomaly, it's about us. The Milky Way's journey toward the Great Attractor is a reminder that no galaxy is an island. We're part of a vast, interconnected web where every tug, every motion traces back to the universe's grand architecture. And when we finally solve this mystery, we won't just uncover what's pulling us, we'll understand our place in the cosmic flow. Cosmic voids aren't just empty space, they're the universe's silent giants, sprawling regions so vast and barren that if you stood at the center of one, you'd need a telescope powerful enough to peer through hundreds of millions of light years just to spot a single galaxy. Take the Boötes Void, a cosmic desert roughly 330 million light years across. Inside its mind-bending emptiness, you'd find only 60 or so galaxies drifting like isolated islands in an ocean of nothingness. Compare that to our own galactic neighborhood, where thousands of galaxies huddle together in clusters, and you start to grasp just how eerie these voids truly are. But here's the puzzle. How did these voids form in the first place? The answer lies in the universe's infancy, when matter wasn't evenly spread but clumped together in a faint cosmic web. As gravity pulled matter into denser filaments and knots, it left behind these gaping holes like the foam in a freshly poured beer, where bubbles form where liquid has drained away. The voids didn't just passively appear, they actively shaped the universe's evolution. Their emptiness creates a counterbalance to the dense galaxy clusters, with the gravitational push of these empty regions subtly steering the motion of superclusters, including our own Milky Way's journey toward the Great Attractor. What's truly bizarre is how these voids behave. Unlike the rest of the cosmos, which is racing apart due to dark energy, voids expand faster than their surroundings. Think of it like stretching a rubber sheet with weights placed on it. The empty areas between the weights stretch more easily, accelerating outward. This runaway expansion has a startling consequence. Over billions of years, galaxies on the edges of voids get pulled into the surrounding filaments, leaving these cosmic deserts even emptier than before. Some models suggest that in the far future, voids could merge into one incomprehensibly large emptiness, with galaxies huddled together in isolated superclusters like campfires in an endless night. Yet for all their emptiness, voids aren't completely lifeless. The handful of galaxies trapped inside them are often strange, lonely objects, some lacking the heavy elements needed to form rocky planets, others drifting through the void like ghost ships, their star formation snuffed out by the lack of fresh gas. These void galaxies are cosmic time capsules, preserving clues about how galaxies evolve in extreme isolation. And then there's the mystery of dark energy. Voids, with their negligible matter content, are perfect laboratories for studying this enigmatic force. If dark energy's strength varies across space, voids might be where its effects are most pronounced, subtly tweaking the expansion rate of the universe itself. The lesson of cosmic voids isn't just about what's absent, it's about balance. The universe isn't just a collection of glittering galaxies. It's a dynamic interplay between the crowded and the empty, the dense and the desolate. Without voids, the cosmic web would collapse under its own gravity. Without their counterweight, galaxy clusters would never have formed. These vast deserts are more than just gaps in the fabric of space. They're the invisible architects of the cosmos, shaping everything from the motion of galaxies to the very fate of the universe itself. And as we map them in greater detail, we're not just studying emptiness, we're uncovering the hidden rhythms of existence, where even nothingness plays a starring role. Intergalactic gas clouds are the universe's hidden reservoirs, drifting like ghostly giants between galaxies, packed with enough raw material to birth entire generations of stars. Take the Smith Cloud, a colossal structure barreling toward the Milky Way at nearly 200 miles per second, stretching over 11,000 light-years long and 2,500 light-years wide. This river of hydrogen carries enough gas to forge 2 million suns, enough to light up a small galaxy. But here's what's truly fascinating. It's not alone. Scattered throughout the cosmic web are countless other clouds, invisible to optical telescopes, their presence betrayed only by the faint glow of radio waves as hydrogen atoms emit their signature 21-centimeter wavelength. These clouds aren't just floating passively, they're dynamic, chaotic, and essential to galactic evolution. Some, like the Smith Cloud, are high-velocity clouds, ejected from galaxies during violent interactions or supernova explosions. Others might be pristine relics from the early universe, pockets of gas that never collapsed into stars, preserving the chemical fingerprints of a time before heavy elements existed. When these clouds collide with galaxies, the results are spectacular. Gas slams into galactic halos, shockwaves ripple through interstellar space, and the sudden influx of fresh fuel can trigger bursts of star formation, lighting up galactic outskirts like fireworks. The mystery lies in how many of these clouds remain undetected. Current surveys suggest there could be thousands just in our local galactic neighborhood, each one a potential stellar nursery waiting to be discovered. The problem: hydrogen's faint signal is easily drowned out by cosmic noise, and without stars or dust to illuminate them, these clouds are like shadows against a dark canvas. New radio telescopes, like the Square Kilometre Array, promise to change that, scanning the skies with unprecedented sensitivity to map this hidden infrastructure of the cosmos. But the real intrigue isn't just in their existence, it's in their role as cosmic recyclers. When galaxies collide, or when supernova blast gas into intergalactic space, these clouds become the universe's way of redistributing raw materials. The oxygen in your lungs, the iron in your blood, even the calcium in your bones, all of it likely spent time drifting in such a cloud before being swept up into a new generation of stars and planets. They're the universe's way of ensuring nothing goes to waste, turning the debris of dying stars into the building blocks of new worlds. What's humbling is realizing these clouds aren't just bystanders in the cosmic story. They're active players, shaping the destiny of galaxies by controlling when and where stars are born. The Smith Cloud might be on a collision course with the Milky Way, but its arrival won't be catastrophic, it'll be creative. In 100 million years, its gas could ignite a dazzling burst of star formation, painting our galaxy's outskirts with new light. And somewhere in that stellar nursery, a future solar system might form, its planets carrying the same potential for life as ours. These invisible giants remind us that the universe isn't just about what we can see, it's about the unseen forces quietly weaving the next chapter of existence. Exoplanet atmospheres are more than just layers of gas, they're chemical fingerprints, revealing secrets about worlds so distant we'll never see them directly. Think of sunlight passing through a stained glass window, its colors altered by the pigments in the glass. Now replace the window with a planet's atmosphere and the light with a star's glow. As that light filters through alien skies, molecules like water vapor, methane, and carbon dioxide absorb specific wavelengths, leaving behind telltale dips in the spectrum, a cosmic barcode we can decode from light years away. The James Webb Space Telescope has turned this technique into an art form. Take K2-18b, a Neptune-sized exoplanet 120 light-years away. Webb's infrared eyes detected water vapor and methane swirling in its atmosphere, but the real shock came with the possible presence of dimethyl sulfide, a molecule on Earth produced only by living organisms. It's not proof of life, but it's the kind of clue that sends scientists scrambling for follow-up observations. And then there's TRAPPIST-1e, a rocky world in its star's habitable zone where future Webb observations might spot ozone or oxygen gases that, on our planet, are almost exclusively tied to biology. But reading these cosmic barcodes isn't as simple as it sounds. An atmosphere isn't just a static layer. It's a dynamic system where winds whip at thousands of miles per hour, where storms the size of continents rage for centuries, and where high-altitude hazes can mask the signals we're desperate to detect. Even the star's activity complicates things. Solar flares can strip atmospheres away or mimic chemical signatures. That's why astronomers don't just look for one gas, they hunt for combinations. Oxygen alone might hint at life, but oxygen alongside methane, two gases that normally destroy each other, suggests something is constantly replenishing them, like photosynthesis or volcanic activity. The most tantalizing targets aren't necessarily Earth twins. Sub-Neptunes, planets between Earth and Neptune in size, might have hydrogen-rich atmospheres that act like massive greenhouses, trapping heat so efficiently that even far from their stars, they could host liquid water oceans beneath thick, swirling skies. Or consider tidally locked worlds, where one side eternally faces its star, creating permanent day and night sides with winds ferrying heat between them, a setup that could spread life-sustaining temperatures across the Terminator line. What's revolutionary is how quickly this field is moving. A decade ago, we knew almost nothing about exoplanet atmospheres. Now, with Webb and upcoming missions like the Habitable Worlds Observatory, we're on the verge of answering humanity's oldest question: are we alone? Every new spectrum is a Rosetta Stone, translating the language of light into the story of distant worlds. And if one of those stories includes a gas that shouldn't exist without life, that's when everything changes, not just for science, but for how we see our place in the cosmos. The universe isn't just building planets, it's painting their skies with clues, waiting for us to look up and decode them. Rogue planets are the ultimate cosmic nomads, worlds untethered to any star, drifting through the galaxy's dark voids like ghost ships in the night. Imagine Earth ripped from the sun's embrace, hurled into interstellar space, its oceans freezing over as sunlight fades to a distant memory. Now multiply that by billions, and you begin to grasp the scale of these wandering worlds. Unlike planets snug in their solar systems, rogue planets don't orbit stars. They're free-floating, ejected from their birthplaces by gravitational chaos or born alone in the cold collapse of gas clouds. And here's the twist: some of them might not be dead wastelands at all. Take CFB Sir 2149-0403, a rogue planet just 100 light-years away. Despite floating far from any star, it's surprisingly warm, about 400 degrees Celsius, its heat left over from a violent birth or simmering radioactive elements in its core. But the real intrigue lies in colder, Earth-sized rogues. Deep beneath their icy surfaces, tidal forces or radioactive decay could maintain vast liquid oceans, shielded from the freezing void above. Europa and Enceladus, the famous ocean moons in our solar system, prove that liquid water doesn't need sunlight to persist. A rogue planet with similar internal heating might harbor hydrothermal vents, those same geological hotspots where life potentially thrives on Earth's seafloor. The numbers are staggering. Simulations suggest there could be 20 times more rogue planets in the Milky Way than stars trillions of worlds adrift in the darkness. Some might be ice giants like Neptune, ejected during their system's turbulent youth. Others could be rocky, Earth-mass planets flung into the abyss by collisions or passing stars. The darkest ones, barely larger than Jupiter, might even mimic stars themselves, glowing faintly from the heat of their slow contraction. And then there's the wild card, primordial rogue planets, formed directly from collapsing gas clouds rather than stellar nurseries. These cosmic orphans could be nearly as old as the universe itself, time capsules from an era before the first stars flickered to life. Detecting these wanderers is like finding needles in a galactic haystack. Without starlight to illuminate them, they're invisible to traditional telescopes, but astronomers have tricks. Microlensing, where a rogue planet's gravity briefly bends light from a background star, has revealed a handful of candidates. Others emit faint thermal radiation, detectable by infrared telescopes like JWST. The upcoming Nancy Grace Roman Space Telescope could uncover thousands more, mapping their distribution and even spotting moons that might cling to them. Now for the million-dollar question, could life exist on these frozen nomads? It's a long shot, but not impossible. Earth's extremophiles thrive in pitch-black ocean depths, near scalding vents or buried under Antarctic ice. A rogue planet's subsurface ocean, rich in minerals from hydrothermal systems, might offer similar niches. The lack of sunlight wouldn't matter to chemosynthetic organisms, which derive energy from chemical reactions rather than photosynthesis. Even radiation from decaying elements could provide energy, much like it does for bacteria in Earth's deepest mines. But the ultimate test would be finding biosignatures, gases like methane or oxygen that hint at biological activity. If a rogue planet's ocean vents gases through cracks in its icy shell, future telescopes might detect those molecules in its thin, transient atmosphere. The discovery would rewrite the rules for habitable zones, proving life doesn't need a star's warmth, just liquid water, chemistry, and time. Rogue planets challenge everything we assume about cosmic neighborhoods and habitability. They're proof that the universe is wilder than we imagined, full of worlds that defy categorization. Some might be frozen relics of lost systems, others dark incubators for life we can't yet fathom. And as we uncover more of these drifters, we're forced to confront a humbling truth. The galaxy isn't just about stars and their planets. It's also about the unseen wanderers, the orphans of gravity, silently carving their own paths through the eternal night. White dwarfs hide a secret at their cores, not just the remnants of burned-out stars, but something far more dazzling. After exhausting their nuclear fuel, these stellar embers slowly cool over billions of years, their carbon-rich interiors compressing under such extreme pressure that atoms lock into a crystalline lattice. The result, a diamond the size of a planet, glittering unseen in the cosmic dark. Consider this: The nearest white dwarf to Earth, Sirius B, is a dense relic packing the Sun's mass into a sphere no larger than our planet. As it cools, its core may already be solidifying into a diamond-like structure, but Sirius B is just one of billions. Across the Milky Way, astronomers estimate that roughly 10% of all white dwarfs, around 300 million, could eventually crystallize into these celestial gems. Some might even be pure enough to rival the clarity of diamonds found on Earth, their atomic perfection untouched by impurities. The process is as mesmerizing as it is slow. When a star like our Sun dies, it sheds its outer layers, leaving behind a searing hot core that gradually radiates away its heat. Over trillions of years, far longer than the current age of the universe, the carbon and oxygen at its heart would theoretically form a near-perfect crystal lattice. But here's the catch: we don't need to wait that long to spot the signs. Even in their early cooling phases, white dwarfs exhibit a telltale, freezing signal, a sudden slowdown in temperature decline as their cores begin the transition from liquid to solid. It's like watching molten steel cool into a rigid blade, only on a cosmic scale. Now imagine one of these stellar diamonds drifting through space, its surface cooled to a few thousand degrees, still scorching by human standards, but frigid for a star. If you could somehow mine it, a feat requiring technology far beyond our grasp, the sheer volume of crystallized carbon would dwarf all the diamonds ever mined on Earth. The largest could rival the mass of Jupiter, compressed into a sphere just a few thousand miles wide. Yet the real wonder isn't just their existence, it's what they reveal about the universe's future. Given enough time, every white dwarf will crystallize, eventually fading into cold, dark, black dwarfs. These cosmic diamonds will outlast galaxies, surviving long after stars burn out and black holes evaporate, becoming the last visible relics of a vanished cosmos. They're not just curiosities, they're time capsules preserving the remnants of stars in a form that could endure for eternity. And here's the kicker: we might have already found one. In 2004, astronomers discovered BPM 37093, a white dwarf nicknamed Lucy after the Beatles song. Its oscillations suggest its core has begun crystallizing, hinting at a diamond-like interior. While we can't see inside, the data paints a picture of a celestial jewel box waiting to be unlocked. So the next time you gaze at the night sky, remember, scattered among those twinkling lights are the universe's greatest treasures, forged in the hearts of dead stars. They're reminders that even in death, stars leave behind beauty, a glittering legacy written in carbon and time. Kilonovas don't just create gold, they're cosmic alchemists, forging the rarest elements in the universe in a heartbeat of unimaginable violence. Picture the aftermath of two neutron stars colliding, a fireball of neutrons so dense that atomic nuclei are ripped apart and rebuilt into exotic forms. In this nuclear crucible, conditions are so extreme that atoms capture neutrons faster than they can decay, climbing the periodic table to form substances like platinum, uranium, and even elements we've barely glimpsed on Earth. The kilonova's glow isn't just light, it's a fingerprint of creation, each wavelength revealing newly minted elements sprayed into the void. Take the kilonova GW170817, detected in 2017. Its spectrum showed clear signatures of strontium, proving these events aren't just about gold. Later studies found hints of even heavier rarities: tellurium, iodine, and possibly actinides like neodymium, elements essential for everything from medical imaging to nuclear reactors. The real shock: some of these substances can't form in supernova at all. Their atomic structures require the unique neutron-rich environment of a kilonova, where nuclei are bombarded by trillions of neutrons per second. It's like trying to build a skyscraper in a hurricane, yet nature manages it with terrifying precision. But the surprises don't stop there. Theoretical models suggest kilonovas might be factories for elements beyond the periodic table's current limits, so-called super-heavy elements that vanish in fractions of a second under earthly conditions. In the frenzy of a neutron-star merger, nuclei could momentarily stabilize at atomic numbers far higher than anything we've synthesized in labs. While we've yet to detect these ephemeral substances, their potential existence hints at a hidden chapter in nuclear physics, written in the debris of cosmic collisions. What's wild is how efficiently kilonovas distribute their treasures. Unlike supernova, which scatter material unevenly, kilonovas eject heavy elements in focused jets at nearly light speed. These jets act like cosmic spray guns, injecting precious metals directly into interstellar gas clouds. Some simulations show that a single merger could seed an entire galaxy neighborhood with enough gold to coat every planet a meter thick. Over billions of years, these enriched clouds collapse into new stars and planets, meaning the iron in your blood and the platinum in your smartphone might trace back to different kilonova events, each contributing its own elemental signature to the galactic mix. The implications stretch beyond chemistry. Kilonovas might solve the mystery of why some stars are born metal-rich while others remain pristine. In regions peppered by ancient mergers, star-forming gas would carry a heavier elemental load, altering how planets form and even which molecules can arise. Life, as we know it, relies on elements like phosphorus and molybdenum, substances that might owe their cosmic abundance to these violent events. Yet for all their destructive power, kilonovas are also creators. Every time we detect one, we're witnessing the universe's way of recycling itself, turning the corpses of dead stars into the building blocks of new worlds. The gold in your jewelry, the uranium powering cities, even the iodine in your thyroid, all of it was likely forged in a flash of light so brilliant it outshone galaxies. These explosions aren't just fireworks, they're the universe's way of ensuring that nothing, not even the heaviest elements, goes to waste. And as we uncover more of their secrets, we're not just studying distant cataclysms, we're piecing together the origin of everything tangible around us, from the phone in your hand to the blood in your veins. Fast radio bursts are the universe's most enigmatic flashes, blindingly bright radio signals that erupt with the power of 500 million suns, then vanish in less time than it takes to blink. Imagine tuning a radio telescope to the cosmos and suddenly catching a burst so intense it outshines every other source in the sky, only for it to disappear before you can even gasp. That's the essence of these fleeting cosmic whispers, first discovered in 2007 and still defying explanation. Some burst once and are never heard from again. Others, like FRB 121102, repeat at irregular intervals, taunting astronomers with clues that only deepen the mystery. The most compelling theories read like a sci-fi anthology. One leading idea points to magnetar's neutron stars with magnetic fields so strong they could strip the data from a credit card halfway across the Milky Way. When these stellar powerhouses undergo starquakes, their crusts crack, releasing energy that could manifest as fast radio bursts. Then there's the cosmic collision scenario, neutron stars smashing into black holes or asteroids vaporizing in the crushing gravity of dense stellar remnants. Even more exotic possibilities lurk in the shadows. Could some bursts be the signatures of advanced alien civilizations beaming propulsion energy across galaxies, or the echoes of cosmic strings vibrating through space-time? What makes these bursts invaluable isn't just their mystery, it's what they carry with them. As fast radio bursts traverse the cosmos, they interact with the sparse electrons between galaxies, slowing slightly in ways that reveal the universe's hidden matter. This dispersion measure acts like a cosmic odometer, letting astronomers map the otherwise invisible web of intergalactic plasma. The record holder, FRB 202200610A, traveled 8 billion light-years before reaching Earth, its journey painting a portrait of the universe's structure during its toddler years. Yet the real puzzle lies in the repeaters. Why do some sources, like FRB 180916, fire off bursts every 16 days with clockwork precision, while others erupt chaotically? One tantalizing explanation involves processing magnetars neutron stars wobbling like spinning tops, their beams sweeping across our line of sight at predictable intervals. Others suggest binary systems where a neutron star's eruptions are modulated by an orbiting companion. Each new detection adds another piece to the puzzle, but the full picture remains stubbornly out of reach. The hunt for answers is accelerating. Telescopes like CHIME in Canada now catch dozens of bursts monthly, while projects like the Deep Synoptic Array in California pinpoint their origins to specific galaxies. Some bursts trace back to serene spiral galaxies like our own, others to chaotic star-forming regions or even the outskirts of galaxy clusters. This diversity hints that multiple mechanisms might be at play, a cosmic menagerie of sources waiting to be catalogued. What's thrilling is realizing how much we don't know. Fast radio bursts remind us that the universe still holds phenomena beyond our wildest theories. Whether they're the death throes of exotic stars, the hum of alien megastructures, or something entirely unimagined, each burst is a postcard from the cosmic unknown, a reminder that discovery isn't just about answers. It's about learning how to ask better questions. The Hubble tension isn't just a scientific discrepancy, it's a cosmic riddle threatening to upend our understanding of the universe's very fabric. Picture two groups of detectives measuring the same crime scene, one using footprints and the other security footage, only to realize their clues point to entirely different timelines. That's the dilemma cosmologists face today. On one side, we have the Planck satellite's meticulous maps of the cosmic microwave background, the afterglow of the Big Bang, suggesting the universe expands at 67 kilometers per second per megaparsec. On the other, the Hubble Space Telescope's observations of pulsating stars and supernova insist the rate is 73, a gap too wide to dismiss as mere error. This isn't just about numbers, it's a potential crack in the foundation of modern physics. For decades, the lambda-CDM model, our gold standard for cosmology, has woven dark energy, dark matter, and ordinary matter into a seamless tapestry explaining everything from galaxy formation to the universe's large-scale structure. But the Hubble tension pulls at its threads. If the discrepancy is real, not some systematic error, it implies something fundamental is missing. Maybe dark energy isn't constant but evolves over time, growing stronger or weaker in ways we haven't accounted for. Or perhaps dark matter interacts with itself or ordinary matter in unexpected ways, subtly altering the expansion rate. Some theorists even speculate about entirely new particles or forces that left no trace in earlier experiments, but now whisper their presence through this mismatch. The most tantalizing possibility, we're seeing hints of a deeper layer of physics, one that operated only in the universe's infancy. Imagine the early cosmos as a stretchy fabric with properties we've never encountered, a brief period where space itself stretched differently, leaving an imprint that now manifests as conflicting expansion rates. Others propose more radical ideas, like our universe colliding with another in a higher dimensional space, injecting extra energy that sped up local expansion. While these theories sound like science fiction, they're grounded in rigorous math, born from scientists' desperation to reconcile the irreconcilable. What's at stake isn't just academic. Resolving the tension could unveil entirely new cosmic ingredients or rewrite the rules governing them. Future telescopes like the Roman Space Telescope and the Vera Rubin Observatory are joining the hunt, cross-checking measurements with novel techniques, gravitational lensing time delays, baryon acoustic oscillations, even gravitational waves from colliding neutron stars. Each method is a new lens offering fresh angles on the problem. Yet the real lesson here is humility. For all our advancements, the universe still holds mysteries that defy our frameworks. The Hubble tension isn't a crisis, it's an invitation. An invitation to look deeper, question harder, and embrace the thrilling possibility that the cosmos still has secrets left to spill. Whether the answer lies in tweaking existing theories or forging entirely new ones, one thing's certain: the solution won't just fix a number, it'll redefine how we see reality itself. Galactic cannibalism sounds like something from a science fiction nightmare, but it's one of the universe's most common and transformative events. Picture two galaxies, each containing billions of stars, locked in a slow-motion dance of destruction and rebirth. Gravity pulls them inexorably closer, their spiral arms twisting into chaotic streams of starlight as they merge into a single, even larger galaxy. This isn't some rare cosmic catastrophe, it's how galaxies grow. Our own Milky Way bears the scars of past meals, with the remnants of devoured dwarf galaxies still visible as stellar streams arcing across the night sky. And in about 4 billion years, we'll be on the menu ourselves when the Andromeda galaxy crashes into us, triggering a celestial firestorm that will reshape both galaxies forever. But what actually happens to stars during these colossal collisions? Contrary to what you might expect, it's less like a demolition derby and more like a carefully choreographed ballet. The distances between stars are so vast that direct collisions are almost unheard of. Instead, stars slide past one another, their orbits scrambled by the shifting gravitational tides. Imagine tossing two handfuls of sand into the air. While the grains mingle, individual particles rarely collide. That's how stars behave during a merger. The real chaos unfolds in the gas and dust between them. These clouds slam together, triggering shock waves that ignite bursts of new star formation, painting the merging galaxies with blue-hot young stars. The aftermath is even more fascinating. Large galaxies like Andromeda and the Milky Way are surrounded by halos of dark matter, invisible, mysterious stuff that makes up most of their mass. When galaxies merge, these halos intertwine like ghostly cobwebs, their gravity sculpting the new galaxy's shape. Sometimes the result is a messy, irregular galaxy. Other times, the merger smooths out into a majestic elliptical galaxy, a golden orb of aging stars. Our own Milky Way has likely undergone dozens of these mergers over its lifetime, growing from a modest collection of stars into the spiral giant we call home today. And here's the twist: these mergers aren't just about destruction, they're also about creation. The violent interactions stir up gas clouds that would have otherwise remained dormant, sparking waves of starbirth. Some of the universe's brightest starburst galaxies owe their brilliance to past collisions. Even our solar system might owe its existence to a long-ago merger that shook loose the gas and dust needed to form the sun and planets. The dance isn't over yet. Right now, the Milky Way is in the process of tearing apart the Sagittarius dwarf galaxy, its stars strewn across our skies in faint, looping trails. And when Andromeda finally arrives, the collision will fling some stars into intergalactic space while others are hurled into new, chaotic orbits. Yet through it all, life on Earth, if it still exists, might barely notice. The night sky will transform, filling with dazzling new stars and nebulae, but the chances of our solar system being disrupted are vanishingly small. Galactic cannibalism isn't just a spectacle, it's a reminder that the universe is in constant flux, with galaxies growing, evolving, and recycling themselves over eons. Every time we look up at the stars, we're seeing the aftermath of these ancient feasts and the prelude to collisions yet to come. The cosmos doesn't stand still, and neither do the galaxies within it. They're always moving, always merging, always writing the next chapter in their violent, beautiful history. Supermassive black holes shouldn't exist in the early universe, and yet there they are. Take J03131806, a cosmic behemoth weighing in at 1.5 billion suns, blazing just 670 million years after the Big Bang. That's like finding a skyscraper in the middle of the Stone Age. Conventional black hole formation can't explain this star's collapsing into stellar mass black holes, then slowly merging and accreting over billions of years. Too slow, the math doesn't add up, so how did these monsters get so big so fast? The answer might rewrite our understanding of cosmic dawn. One radical idea. Direct collapse black holes. Imagine a primordial gas cloud, untouched by heavy elements, collapsing under its own weight so violently it skips the star stage, entirely plummeting straight into a black hole with tens of thousands of solar masses right out of the gate. These seeds would have a head start, gorging on surrounding gas and merging with others to reach supermassive status in cosmic record time. The trick is the gas. Without metals to cool and fragment it, the cloud stays monolithic, collapsing in one catastrophic plunge. Telescopes like JWST are now hunting for traces of these rare, pristine clouds in the early universe, where the chemistry was just right for such extreme birth scenarios. But there's another twist. What if some black holes didn't grow from the bottom up, but were born big? Theories involving quantum fluctuations or exotic phases of the early universe suggest spacetime itself might have birthed massive black holes directly during cosmic inflation. Picture bubbles of ultra-dense space pinching off like droplets, each one a black hole nursery. It's speculative, but if true, it would mean supermassive black holes weren't just early arrivals. They were part of the universe's blueprint from the very beginning. The stakes are higher than just solving a cosmic puzzle. These ancient black holes shaped their galaxies, their radiation carving out ionized bubbles that influenced star formation across the early cosmos. Some might even persist today as wandering intermediate mass black holes, lurking unseen in galactic halos. And if we can pin down their origins, we'll unlock secrets about the universe's most chaotic era, a time when the rules of physics as we know them might have bent just slightly to build the impossible. Every new detection pushes the mystery deeper. Euler's J1342 plus 0928, another early universe quasar, tips the scales at 800 million suns when the universe was barely 700 million years old. How maybe runaway collisions in dense star clusters, or freakishly efficient feeding frenzies in gas-rich environments, or perhaps something we haven't even imagined yet. One thing's certain, these cosmic anomalies aren't glitches in the system. They're clues, whispers from an era when the universe worked differently, playing by rules we're only beginning to glimpse. Exomoons might be the universe's best-kept secret, hidden worlds orbiting alien planets, some with conditions ripe for life, others defying everything we know about celestial mechanics. Consider this: for every exoplanet we've discovered, there could be multiple moons lurking in their gravitational embrace, each one a potential game-changer in the search for life beyond Earth. Take Kepler 1625b, a gas giant in its star's habitable zone. While the planet itself is inhospitable, any large moon in its orbit could bask in just the right amount of warmth for liquid water to pool on its surface, mirroring the icy oceans of Europa or Enceladus in our own solar system. Detecting these elusive satellites isn't just a technical challenge, it's a cosmic needle in a haystack hunt. Unlike planets, which cast clear shadows as they transit their stars, exomoons are smaller, fainter, and often drowned in their host planet's glare. But astronomers have tricks. When a moon orbits a planet, it tugs on it ever so slightly, causing tiny wobbles in the planet's transit timing or duration. These minute disruptions, called transit timing variations, are like fingerprints betraying the moon's presence. Another method looks for secondary dips in starlight, the faint shadow of a moon trailing its planet like a cosmic duckling. The real prize, an exomoon with its own atmosphere. Imagine a world like Titan, but orbiting a distant gas giant, its skies thick with nitrogen and methane, its surface dotted with hydrocarbon lakes. Such a moon wouldn't just be a scientific curiosity, it could be a laboratory for probiotic chemistry, showing us how life might arise under radically different conditions. The best candidate so far, Kepler 1625b, still awaits confirmation, but its potential existence has already ignited debates about how atmospheres form and persist around moons, especially those bathed in intense radiation from nearby stars. But here's the twist: not all exomoons would be life-friendly. Some might be tidally locked hellscapes, one side scorched by their star, the other frozen in eternal night. Others could orbit rogue planets, untethered to any star, their surfaces warmed only by tidal forces or radioactive decay. And then there are the theoretical supermoons, massive, planet-sized satellites that could rival Mars in scale, their gravity strong enough to hold onto thick atmospheres for billions of years. The implications stretch far beyond habitability. Exomoons could rewrite the rules of planetary formation. In our solar system, moons like Ganymede and Titan formed alongside their planets from leftover debris. But around other stars, moons might be captured alien worlds snatched from their original orbits and pressed into service as satellites. Some might even be remnants of colossal collisions, born from the debris of two planets smashing together, much like our own moon. With next-generation telescopes like the James Webb Space Telescope and the upcoming Extremely Large Telescope, the first confirmed exomoon detection could be just around the corner. And when it happens, it won't just add another entry to the catalogue of celestial objects, it'll open an entirely new frontier in astrobiology, planetary science, and our understanding of how common or rare life-bearing worlds truly are. The universe has already shown us it's full of planets. Now we're on the verge of discovering its hidden lunar kingdoms, each one a world unto itself, waiting to tell its story. The universe doesn't just build planets around stars, it flings them into the void, sending rocky wanderers like Oumuamua careening between galaxies like cosmic tumbleweeds. When this mysterious object streaked past Earth in 2017, it shattered assumptions. Here was no ordinary comet or asteroid, but something far stranger. The first confirmed visitor from another star system, shaped like a pancake, tumbling end over end and accelerating in ways that defied simple explanation. Was it a shard of a shattered alien world, a hydrogen iceberg evaporating in sunlight, or, as some daring theorists suggested, a relic of extraterrestrial technology? The truth remains elusive, but one thing's certain: Oumuamua was just the beginning. What made this interstellar interloper so baffling wasn't just its origin, it was its behavior. Unlike comets, which spew gas and dust to form visible tails, Oumuamua showed no such activity, yet its trajectory subtly deviated as if nudged by unseen forces. One explanation: outgassing hidden jets of vaporizing material pushing it off course. But there's a catch: no telescope caught even a whisper of gas or dust around it. Another possibility: solar radiation pressure, the faint push of sunlight, could have propelled it if the object was unusually light and thin, like a solar sail. That's where the wilder theories took root. Could Oumuamua have been artificial? The odds are vanishingly small, but the mere possibility forced scientists to confront how little we know about what lurks between the stars. Since Oumuamua's departure, we've spotted more interstellar nomads. Borisov, a rogue comet with a distinct chemical fingerprint, barreled through in 2019, its tail rich in carbon monoxide, a clue it formed in a frigid, alien star system. Unlike Oumuamua, Borisov was unmistakably a comet, its icy heart vaporizing as it neared the sun. Together, these visitors paint a startling picture. Interstellar space might be teeming with free-floating objects, some ejected during the chaotic births of planetary systems, others perhaps the remnants of cosmic collisions. The real revolution is coming. Telescopes like the Vera Rubin Observatory, set to scan the entire southern sky every few nights, will likely catch dozens more of these drifters in the next decade. Each one is a time capsule carrying chemical signatures from its home system. Some might even harbor ices or minerals impossible to form in our solar system, offering a taste of how alien planets are built. There's even a chance we'll find one parked in our own backyard, an interstellar rock captured by the sun's gravity, hiding in plain sight among asteroids. But the grandest question remains, could these visitors carry life? It's a long shot, but not impossible. If microbial life can hitchhike on meteorites, as some theories suggest, perhaps extremophiles lie dormant inside interstellar objects, frozen for eons between stars. The idea isn't pure fantasy. NASA, a Stardust mission already caught amino acids, life's building blocks, on a comet from our own solar system. An interstellar traveler might carry even more exotic chemistry, a snapshot of biology's potential elsewhere in the cosmos. Oumuamua and Borisov weren't just scientific curiosities, they were messengers, proof that the universe is more restless, more interconnected than we ever imagined. The next time one of these wanderers streaks past, we'll be ready not just to watch but to chase. Missions like the European Space Agency's Comet Interceptor aim to lie in wait, poised to launch at a moment's notice when the next interstellar guest arrives. Because out there, in the dark between stars, countless more drift unseen, each one a piece of a puzzle we're only beginning to assemble. And every new discovery won't just tell us about them, it'll reveal something profound about our place in a galaxy that's far from empty. The Milky Way isn't just a serene spiral of stars, it's a cosmic pressure cooker, and proof of its explosive past towers above and below its center in the form of the Fermi bubbles. Picture two colossal orbs of scorching hot gas, each stretching 25,000 light-years from the galactic plane, pumping out gamma rays like cosmic lighthouses. These aren't subtle features, they're titanic geysers of energy, dwarfing everything else in our galaxy. And the most startling part, they're invisible to the naked eye, revealed only by telescopes tuned to the high-energy wavelengths of gamma radiation. What could blast such enormous structures into existence? The prime suspect sits at the very heart of our galaxy, Sagittarius, a star, the Milky Way's supermassive black hole. While it's quiet today, astronomers suspect it wasn't always so well behaved. Roughly 3.5 million years ago, a cataclysmic feast may have taken place. Imagine a massive gas cloud or even a star straying too close, torn apart by tidal forces as it spiraled toward oblivion. The resulting accretion disk would have become a particle accelerator on a galactic scale, funneling unimaginable energy into twin jets that punched through the galaxy's gas halo, inflating these bubbles like cosmic balloons. But here's where it gets even wilder. The Fermi bubbles aren't just fossils, they're still active. Observations show their edges crackling with shock waves, suggesting they're either still growing or reverberating from a more recent energy injection. Some theories propose multiple eruptions over time, like a black hole belching periodically after particularly large meals. Others point to star formation frenzies near the galactic center, where thousands of supernovae could have combined their might to blow these bubbles in a coordinated stellar uprising. The implications stretch far beyond our galaxy. If the Milky Way's black hole could unleash such violence, what does that mean for more active galaxies, like quasars with black holes hundreds of times more massive? Their Fermi bubble equivalents could span entire galaxy clusters, shaping intergalactic space for millions of light years. Even our own bubbles might have left scars on nearby dwarf galaxies, their outer edges scoured by the Milky Way's ancient outbursts. Yet the biggest mystery isn't just how these bubbles formed, it's what they're made of. Spectroscopy reveals they're laced with high-speed protons, electrons, and maybe even dark matter particles, all zipping around at nearly light speed. This cosmic soup is a natural particle collider, offering clues about how the universe accelerates matter to such extreme energies. Future telescopes, like the Cherenkov Telescope Array, could detect even fainter traces of these particles, helping us reconstruct the bubble's birth with forensic precision. What's humbling is realizing we're living in the aftermath of a galactic-scale explosion, nestled in a galaxy that once roared with energies beyond comprehension. The Fermi bubbles are more than just a scientific curiosity. They're a reminder that even the calmest-looking galaxies have violent pasts. And as we piece together their story, we're not just uncovering the Milky Way's history. We're learning how galaxies grow, evolve, and occasionally remind their stars and planets just how small we really are. Planetary nebulae are the universe's farewell masterpieces, the final, breathtaking act of stars like our sun before they fade into cosmic embers. Picture a star having burned steadily for billions of years, finally exhausting its nuclear fuel. As its core contracts, its outer layers puff outward in a slow-motion eruption, transforming into a luminous shroud of gas that glows with colors so vivid they seem painted by an artist's hand. The Helix Nebula, with its eerie blue eye, and the Ring Nebula, a perfect smoke ring suspended in space, are just two of these celestial gems, each one a unique fingerprint of stellar death. But how do these intricate structures emerge from what should be a chaotic, explosive process? The answer lies in the delicate dance between physics and artistry. As the dying star sheds its outer layers, its remaining core, a white dwarf heats up to over 100,000 degrees, bombarding the ejected gas with ultraviolet radiation. This energy excites atoms in the gas, causing them to fluoresce in vibrant hues. Oxygen glows green, nitrogen red, and hydrogen blazes in crimson. The shapes we see aren't random, they're sculpted by hidden forces. Binary companions, magnetic fields, or even planets can carve the expanding gas into delicate tendrils, symmetrical rings, or hourglass figures. The Southern Crab Nebula, for instance, sports intricate loops and knots shaped by a spinning white dwarf and its companion star, like a cosmic potter shaping clay on a wheel. Some nebulae defy expectations entirely. Take the Butterfly Nebula, with its symmetrical wings stretching over 3 light years. This structure likely formed from extreme stellar winds, gusts of charged particles streaming from the star's poles at speeds topping 600 miles per second. These winds collide with slower-moving material ejected earlier, creating shock waves that sculpt the gas into ethereal shapes. Other nebulae, like the Cat's Eye, reveal concentric rings, evidence of the star's final, pulsing death throes where it shed its skin in rhythmic bursts spaced thousands of years apart. What's truly humbling is the fleeting nature of these cosmic artworks. A planetary nebula shines for just a few tens of thousands of years, a blink in cosmic time before its gas disperses into the interstellar void, seeding future generations of stars and planets. The atoms in your body might once have drifted through such a nebula, forged in the heart of a dying star and set adrift to one day become part of Earth or you. And here's the twist: our sun will join this gallery of glowing ghosts. In about 5 billion years, it too will swell, shed its layers, and light up the cosmos with its own ephemeral masterpiece, a final, radiant testament to a star's quiet, enduring legacy. Planetary nebulae aren't just deaths, they're rebirths, reminding us that in the universe, even endings can be dazzling. Hypervelocity stars are the Milky Way's ultimate escape artists, cosmic projectiles hurtling through space so fast they'll eventually leave our galaxy behind entirely. Take SDSS J09's 0745 0 + 02 4507, a star racing outward at over 900 kilometers per second, more than twice the speed needed to break free from the Milky Way's gravitational grip. At that pace, it could cross the distance between New York and Los Angeles in less than 4 seconds. Unlike the orderly orbits of most stars, these speed demons follow chaotic trajectories that trace back to some of the most violent events in the cosmos. Their origin stories read like cosmic thrillers. Some gain their incredible speed from supernova explosions when a massive star dies. The asymmetrical blast can kick its surviving companion star like a slingshot, sending it careening through space. Others owe their velocity to the Milky Way's central black hole, Sagittarius, a star. When binary star systems wander too close, the black hole's immense gravity can tear them apart, capturing one star while flinging the other outward at breathtaking speeds. Picture a gravitational pinball machine where stars become the balls launched at impossible velocities. The diversity of these stellar fugitives is just as fascinating as their origins. While most are blue, hot, and massive stars built for speed, astronomers have spotted yellow sun-like stars and even red dwarfs among their ranks. Each type tells a different story. The massive ones likely got their kick from supernova, while the smaller stars may have been ejected through complex gravitational interactions in dense star clusters. Then there's the curious case of LP 4365, a bizarre, metal-rich star moving fast enough to escape the galaxy, but with a composition suggesting it survived a partial supernova explosion itself, a cosmic phoenix rising from its own ashes. Where does their journey lead? Untethered from galactic gravity, these stars are destined for the freezing void between galaxies. Over millions of years, they'll cross the intergalactic medium, where the density of atoms is so low it makes Earth's best vacuum chambers seem crowded. Some might eventually be captured by another galaxy's gravity, becoming interstellar immigrants in a new stellar society. Others could wander indefinitely, their light fading into darkness as they become lone travelers in an unimaginably vast cosmic ocean. Yet even in their isolation, hypervelocity stars serve a purpose. Their trajectories act as cosmic breadcrumbs, helping astronomers map the Milky Way's gravitational field and the distribution of dark matter. By tracing their paths backward, scientists can identify regions of intense gravitational activity, like previously unknown black holes or dense dark matter clumps. And as telescopes grow more sensitive, we're finding these speedsters aren't as rare as once thought, hinting that the galaxy might be far more dynamic and chaotic than its serene spiral arms suggest. The most poetic twist, our own sun moves through the galaxy at a sedate 230 kilometers per second, its path steady and predictable. But in the grand tapestry of the Milky Way, it's the renegades that reveal the most about the violence of stellar life, the hidden forces shaping our galaxy, and the incredible diversity of cosmic motion. Hypervelocity stars remind us that even in a universe governed by gravity, some objects will always find a way to break free. The Kuiper Cliff is one of the solar system's most perplexing boundaries, a place where the rules of planetary architecture seem to break down without warning. Out beyond Neptune, the Kuiper belt stretches like a frozen junkyard of icy debris, home to dwarf planets like Pluto and thousands of smaller objects left over from the solar system's formation. But then, at roughly 50 astronomical units from the Sun, about 7.5 billion kilometers, the belt's population drops off a cliff. The expected swarm of icy bodies simply vanishes. It's as if someone built a cosmic fence at the edge of our planetary neighborhood and posted a "no trespassing" sign. This abrupt cutoff defies everything we know about how planetary systems form. The outer solar system should be littered with icy remnants, gradually thinning out as you move farther from the Sun. Instead, the Kuiper belt's objects cluster tightly before hitting an invisible wall, leaving astronomers scratching their heads. One leading theory, a hidden planet massive enough to sweep its orbital path clear of debris, might be lurking in the darkness. The hypothetical planet 9, if it exists, could be 10 times Earth's mass, orbiting so far out that a single trip around the Sun takes 20,000 years. Its gravity would act like a cosmic broom, kicking smaller objects into skewed orbits or ejecting them entirely, leaving behind the strange void we observe today. But the hunt for Planet 9 is like searching for a black cat in a coal cellar. The potential signatures are tantalizing but indirect, clusters of Kuiper belt objects with oddly aligned orbits, all tilted in the same direction as if tugged by an unseen hand. Some of these objects even loop backward around the Sun, moving in orbits so extreme they'd be nearly impossible without a massive perturber. Yet despite years of scouring the skies with telescopes like Subaru and Pan-STARRS, no one's found definitive proof. The math suggests where Planet 9 should be, but the cosmos isn't making it easy. Not everyone's convinced a hidden world is the answer. Alternative explanations range from the Kuiper belt's chaotic formation, perhaps the early solar system's gravitational turmoil left it naturally sparse, to the possibility that passing stars in the Milky Way's crowded youth stripped away the outer debris. There's even a wild card idea: primordial black holes, no larger than a grapefruit but as massive as a planet, could be lurking out there, their gravity mimicking a planetary presence without emitting a single photon of light. The stakes are higher than just solving a puzzle. If Planet 9 exists, it would rewrite solar system history, suggesting our cosmic backyard was shaped by a violent, dynamic past we're only beginning to uncover. Its discovery would rank among the most significant in modern astronomy, a reminder that even in our own celestial neighborhood, there are still uncharted territories waiting to be explored. And if it's not there, the Kuiper cliff becomes an even deeper mystery, forcing us to rethink how planetary systems evolve at their fringes. Every new survey, every upgraded telescope brings us closer to an answer. The Vera Rubin Observatory, set to begin scanning the skies in 2025, could be the key. Its relentless gaze might finally spot the faint, slow-moving dot that's eluded us for so long. Until then, the Kuiper cliff stands as a silent sentinel, guarding the threshold between the known and the unknown, daring us to look deeper into the dark. Dark galaxies lurk in the cosmic shadows, entire islands of stars so faint they blend into the blackness of space, their presence betrayed only by the subtle warping of light around them. These ghostly structures, like the infamous Dragonfly 44, contain barely 1% the visible matter of a typical galaxy, yet somehow weigh as much as the Milky Way. The missing mass, a monstrous halo of dark matter, invisible and mysterious, holding these wispy collections of stars together against all odds. It's as if someone took a normal galaxy and erased 99% of its stars, leaving behind only a fragile skeleton of luminous matter swaying in the dark. Finding these cosmic phantoms requires tricks beyond ordinary telescopes. Gravitational lensing, the bending of light around massive objects, acts like nature's X-ray vision, revealing dark galaxies by how they distort the images of background galaxies. The more a galaxy's gravity bends light, the more mass it must contain, even if that mass is invisible. Some of these ghosts, like the lensed galaxy J-VAS-B 1938 plus 666, appear as faint smudges in optical light but reveal their true heft when their gravitational fingerprints are measured. Others, like the ultra-diffuse galaxies in the Coma cluster, float like jellyfish in space, their stars so spread out you could fly through one and barely notice. Why do these shadowy giants exist? One theory suggests they're failed galaxy structures where gas never condensed enough to birth stars in large numbers, leaving them frozen in an embryonic state. Another idea posits they're the survivors of violent encounters, their stars ripped away by tidal forces while their dark matter halos remained intact. The most tantalizing possibility, they might be relics from the early universe, pristine examples of how galaxies looked before multiple mergers bulked them up with stars. If true, they're cosmic time capsules, preserving secrets about how dark matter shaped the first galactic building blocks. The implications are profound. If dark galaxies are common, they could solve the missing satellite problem, the puzzling shortage of small galaxies orbiting the Milky Way compared to dark matter simulations. Maybe we've been looking for them wrong. Perhaps these satellites aren't missing at all, just too dark to see. Future telescopes like the Vera Rubin Observatory could uncover thousands more, mapping their distribution and testing whether they truly are the universe's silent majority. But the real mystery isn't just their existence, it's what they're made of. Some dark galaxies, like Antlia 2, seem to be dissolving, their dark matter halo mysteriously puffed up and diffuse compared to predictions. Others show bizarre star-forming activity in their sparse gas clouds, defying expectations about how star birth should work in such extreme environments. Each discovery chips away at our assumptions, forcing us to rethink how galaxies live, die, and sometimes fade into the shadows without ever shining brightly at all. What's humbling is realizing how much of the universe might be hiding in plain sight. For every glittering spiral like Andromeda, there could be dozens of these spectral counterparts, drifting unseen at the edges of our cosmic awareness. They're reminders that the night sky, for all its brilliance, is just the visible tip of a much darker, stranger iceberg, one we're only beginning to explore. The cosmic microwave background is more than just ancient light, it's the universe's baby picture, a snapshot of the cosmos when it was a mere 380,000 years old. Imagine the universe as a newborn, finally cool enough for photons to break free from the charged plasma that had trapped them since the Big Bang. That first burst of light, stretched and faded over 13 billion years, now reaches us as a faint microwave glow, bathing the entire sky in a whisper of creation. But hidden within this afterglow are secrets about how the universe grew up, tiny temperature variations no stronger than 100,000th of a degree, yet powerful enough to shape everything from galaxies to superclusters. These fluctuations aren't random noise, they're cosmic blueprints, the slightly denser regions where the microwave background is a fraction warmer, mark the seeds where gravity would later pull matter into galaxies and clusters. The cooler spots, those are the future homes of cosmic voids, the vast empty deserts between galactic threads. It's staggering to think that the entire large-scale structure of the universe, every galaxy, every filament of the cosmic web, was imprinted in these infinitesimal wrinkles, like the grooves on a vinyl record holding the symphony of existence. What's even more astonishing is how perfectly this light matches theoretical predictions. The patterns align with a universe made up of 5% ordinary matter, 27% dark matter, and 68% dark energy, numbers that now form the bedrock of modern cosmology. But the cosmic microwave background doesn't just confirm what we know, it also hints at what we don't. Anomalies like the cold spot, a strangely frigid patch spanning over 1 billion light-years, defy easy explanation. Could it be a shadow cast by a parallel universe brushing against ours, or the imprint of a cosmic defect, a crack in spacetime's fabric left over from the Big Bang? Then there's polarization, the subtle directional twist in the light that tells us about the universe's violent infancy. Certain swirls in this polarization, called B modes, could carry echoes of primordial gravitational waves, ripples in spacetime itself from the universe's exponential growth spurt during cosmic inflation. Detecting these signals is like listening for the faintest whisper in a thunderstorm, but if confirmed, they'd offer direct proof of the universe's explosive beginnings. Projects like the Simons Observatory and next-generation space telescopes are racing to capture these elusive fingerprints, hoping to unlock the conditions of the universe's first trillionth of a second. Yet the cosmic microwave background isn't just a relic, it's still shaping the cosmos today. As light from distant galaxies passes through these ancient temperature variations, it gets slightly deflected, a phenomenon called the integrated Sachs-Wolf effect. This subtle distortion lets astronomers map dark matter's distribution in 3 dimensions, turning the afterglow into a tool for probing the invisible scaffolding of the universe. What's humbling is realizing this light has been traveling since before Earth, the Sun, or even the Milky Way existed. It's a message from a time when the universe was a hot, dense soup of particles, before stars lit the darkness, before planets formed, before life evolved to wonder about its origins. And as we decode its secrets, we're not just studying the past, we're uncovering the foundation of everything that came after, from the first galaxies to the planet beneath our feet. The cosmic microwave background isn't just a window into the universe's infancy, it's the mirror that reflects our own cosmic ancestry. Multiverse theory isn't just science fiction, it's a legitimate scientific possibility, born from the same equations that describe our universe's explosive birth. Picture the Big Bang not as a single event, but as a cosmic bubble bath where each bubble is a separate universe, inflating endlessly into its own reality. Our entire observable cosmos might be just one frothy pocket in an infinite sea of universes, each with its own unique physics, constants, and even dimensions. Some could have gravity 10 times stronger, others might lack electromagnetism entirely, and a few could harbor life so alien we wouldn't recognize it. The idea isn't just wild speculation. It emerges naturally from inflationary cosmology, the leading theory for how our universe expanded so rapidly in its first moments. The key lies in quantum fluctuations during inflation, tiny ripples in spacetime that got stretched to cosmic scales, seeding the galaxies and voids we see today. But if inflation can happen once, why couldn't it happen eternally, spawning new universes like bubbles in a boiling pot? This eternal inflation scenario, championed by physicists like Alan Guth and Andre Linde, suggests that where inflation stops in one region creating a universe like ours, it continues elsewhere, birthing countless others. Some of these universes might collapse instantly, others could expand so fast that stars never form. Ours, with its Goldilocks perfect balance of forces, might simply be the rare bubble where life could arise to ponder its existence. Testing something as abstract as the multiverse seems impossible after all. If other universes are causally disconnected from ours, how could we ever detect them? Surprisingly, there are ways to hunt for clues. One approach studies the cosmic microwave background for anomalous bruises left by collisions with other bubble universes in the distant past. Imagine two soap bubbles gently bumping in a sink. If our universe grazed another during inflation, the impact could have left a faint, circular imprint in the background radiation. Telescopes like Planck have scoured the data for these signatures, and while nothing definitive has been found, the search continues. Another tantalizing hint comes from dark energy's perplexing value. In our universe, it's inexplicably small, just enough to accelerate expansion without tearing atoms apart. But in a multiverse, dark energy's strength could vary randomly across universes, with most either too weak to matter or so strong that galaxies never form. The fact that we live in a universe where dark energy is oddly life-friendly might be no accident. It could be statistical inevitability, a consequence of us existing in one of the rare bubbles where conditions allow observers to exist. This anthropic reasoning is controversial but forces us to ask, is our universe fine-tuned, or are we just winners of a cosmic lottery? The most radical test might come from quantum mechanics. The many worlds interpretation suggests every quantum decision spawns parallel realities, meaning alternate versions of you exist in branching timelines where every possible outcome plays out. While this version of the multiverse differs from inflationary bubbles, both ideas share a startling implication. Reality is far bigger and stranger than we ever imagined. Future experiments in quantum gravity or high-energy physics might uncover signatures of these hidden dimensions or parallel branes, as predicted by string theory. Skeptics argue the multiverse is untestable metaphysics, a retreat from science's demand for falsifiable evidence. But proponents counter that it's no different from Copernicus suggesting Earth wasn't the center of the solar system, a humbling expansion of perspective. Whether the multiverse is real or not, the theory's true value might lie in how it reshapes our questions. If countless universes exist, each a natural experiment in physics, then the laws we cherish aren't absolute, they're local bylaws, valid only in our cosmic neighborhood. That realization alone forces us to rethink everything from the nature of reality to our place within it. The multiverse isn't just about other worlds, it's about understanding the uniqueness, or perhaps the mediocrity, of our own. Time isn't the steady, universal clock we imagine. It's fluid, bending under the weight of gravity and speed like taffy stretched between cosmic fingers. Einstein's theory of relativity revealed this shocking truth. Near massive objects, time itself slows down, a phenomenon called gravitational time dilation. Picture a clock placed at the edge of a black hole. To a distant observer, its hands would crawl at a glacial pace compared to a clock on Earth, as if time itself were drowning in the black hole's gravitational well. But you don't need a black hole to see this in action. Even Earth's gravity tugs at time enough that GPS satellites, orbiting high above our planet, must constantly correct their clocks. Without these adjustments, your phone's navigation would drift off by nearly 7 miles every single day, a cascade of tiny time discrepancies snowballing into real-world chaos. The real cosmic heavyweights, though, take time dilation to unimaginable extremes. Take neutron stars, city-sized stellar corpses so dense that a teaspoon of their material weighs 1 billion tons. On the surface of one, time slows by about 30% compared to Earth. A single hour there would pass in what feels like 42 minutes back home. But even that pales next to a black hole's event horizon, where gravity warps time so severely that, from an outsider's perspective, a falling object would appear to freeze in place, its light redshifted into oblivion as time grinds to a halt. It's as if the universe itself hits pause at the edge of oblivion, Speed 2 twists time's fabric. Astronauts aboard the International Space Station experience time slightly faster than Earthbound observers, not because of gravity, they're actually in a weaker gravitational field, but because they're hurtling at 17,000 miles per hour. According to special relativity, the faster you move through space, the slower you move through time. Over a 6-month mission, astronauts gain about 5 milliseconds, a tiny difference but proof that time is anything but absolute. Now imagine a starship traveling near light speed. To its crew, a trip to Alpha Centauri might feel like a few years, but back on Earth, decades could pass, a real-life version of the twin paradox where one sibling returns younger than the other. The most mind-bending implication, time dilation isn't just a quirk of physics. It shapes how we see the universe. Light from the early cosmos, stretched by the expansion of space, arrives billions of years later, its wavelengths transformed into the faint microwave hum of the cosmic background radiation. Even the universe's expansion rate, measured by distant supernova, hinges on how time flows differently across cosmic distances. Every time we peer into deep space, we're not just looking across space, we're gazing back through layers of time, each epoch ticking at its own rhythm. And here's the kicker, time dilation might one day be more than just a curiosity. If humanity ever masters near light speed travel, astronauts could reach distant stars within their lifetimes, even if centuries pass on Earth. Black holes, often seen as destructive monsters, could become time machines of sorts. Orbiting one closely would let a spacecraft experience years while millennia unfold elsewhere. The universe, it seems, has built-in loopholes in the flow of time, waiting for us to discover how to navigate them. For now, these effects remain subtle, measurable only with atomic clocks and precise instruments. But they whisper a profound truth. Time isn't the rigid scaffold we imagine. It's a living, breathing dimension, as malleable as the cosmos is vast. And every second that ticks by is proof that relativity isn't just theory, it's the silent architect of reality itself. From the delicate filigree of dark matter halos to the explosive brilliance of kilonovas forging cosmic gold, our journey through these 34 celestial wonders has revealed a universe that defies simple explanation. These aren't just random phenomena, they're the architectural blueprints of existence itself, each structure a testament to the forces that shape reality on scales both unimaginably vast and infinitesimally small. What's remarkable isn't just their grandeur, but how interconnected they are. The same gravity that sculpts galaxy clusters also guides rogue planets on their solitary journeys, while the shockwaves from long-dead stars seed future generations of worlds with the ingredients for life. Standing beneath the night sky, it's easy to see stars as isolated pinpricks of light. But now you know better. That darkness between them, it's alive with structure, a tapestry of filaments and voids, of magnetic fields and quantum fluctuations, all working in concert to build everything from the smallest moon to the largest supercluster. Even the emptiest corners of space hum with potential, whether it's the ghostly whisper of dark matter or the slow crystallization of white dwarfs into cosmic diamonds. The universe isn't just a collection of objects, it's a dynamic, evolving masterpiece where every piece plays a role in the whole, and the most thrilling part. This is just the beginning. For every mystery we've solved, like how neutron star collisions forge heavy metals or why quasars light up the early cosmos, dozens more await. What lurks in the Kuiper Cliff's shadow? Could dark galaxies outnumber the ones we see? Is the Hubble tension a sign of new physics or a clue to deeper layers of reality? The questions aren't just academic, they're invitations to adventure, reminders that exploration doesn't end at the edge of our solar system or even our galaxy. It stretches as far as curiosity can reach, So the next time you look up, remember, you're not just a spectator. You're part of this story, standing on a planet orbiting one star among billions, in a galaxy that's itself a single thread in the cosmic web. The universe built you from its raw materials, and now it invites you to explore it in return. Press subscribe to join us as we chase the next discovery, whether it's hidden in the data of a space telescope or written in the light of a dying star. The cosmos is full of wonders, and the best ones might still be waiting for us to find.